Gerardo, please. The next talk of this morning's session is by Professor Gerardo Adesso from the Nottingham University, and he will speak about a quantum Gibbs paradox. Please, Gerardo.
Thank you very much. Let me just see if I can. No, I think it's fine. Yes. Hi. Well, of course, I would have loved to be there in Argentina with all of you. We just made it to Cordova. I've not been with you the whole 10 years in the past, but I was there in Cordova in 2019. And I think by the time we were doing that conference, probably all this mess was starting in China about the same time. So the world has different plans, and now we're doing this online, but I hope that at least this made it easier for several colleagues to just take part in this event and support the development of quantum foundations in Argentina, which is really promising. And I was really impressed by what I learned 2 years ago, and hopefully what I will learn during this conference. So thanks again for inviting me and for organizing this event.
Thank you, Gerardo. Zoom. Thank you for being here. Thanks.
You're welcome. Right. So what did I talk about 2 years ago was indeed about indistinguishable particles. And in a certain sense, we're still talking about them. But today we're going to give it a rather different spin. So last time we were interested more into whether entanglement between distinguishable particles is a real resource or not. But today we move in even more into the foundational side of things. And the idea is, as most of my research, my interest is in actually trying to work out if there are any boundaries to the quantum world. So this is a nice picture by Zurek. And sometimes I see myself as this little guy patrolling the border between the classical and the quantum world, whichever way we aim to define them. And the idea is that I'm interested in identifying some signatures that are distinctive, and they can only happen in the quantum world, but maybe they get lost once we move out towards the classical world. So there are many of these things. The most famous ones might be superposition, coherence, entanglement, and some of these signatures that are non-localities, you were debating about them, contextuality, and so on. So some of these are uniquely quantum, some others may be features of more general theories, but some others are not replicable in the classical case. Whenever we discover more of some traits which are specific quantum, or definitely non-classical at least, then the idea is not only this is interesting from a foundational point of view, because we get to understand more about the basic building blocks of quantum mechanics, but this also makes it potentially interesting for people working in the development of new technologies, as we have all seen in the past 3 decades. So the more we understand about the nature and the use of quantum features like entanglement and so on, so the more we can empower them as resources for novel applications. So we're interested in both of these things. Today, we're going to look at something quite unusual as a resource. And this something is actually ignorance. So this talk will identify some, I would say, fundamental difference between classical and quantum mechanics in the power of ignorance within the context of thermodynamics. So let me just go back to talking about the Gibbs paradox as it was known in classical thermodynamics first. Right, so the idea is the following. You have a box. So suppose it's initially divided into 2 halves. And then at the beginning, you just have a gas filling 1/2 of this box. I think you can probably see the pointer here on my screen, right? Hopefully. So you have n particles and they fill up this volume V, which is half of the box. Now you open the membrane in the middle and you let the gas expand isothermally to fill the full box, so twice its original volume. Of course, in this process, you have created entropy, and the entropy produced is n ln log 2, where n is the number of particles of gas. But then consider this situation here. Suppose from the beginning you had 2 species of gas, each filling 1/2 of this box, and then you remove the membrane and both of them expand to fill up the whole volume. So if those 2 gases were in some way distinguishable, so they had some property which differentiates one from the other, in this case, they look like 2 different colors. They might have 2 different atomic numbers and so on. So you would say that each of them expands, like the first case, from V to 2V, And so each of them brings in an increase in entropy given by n log 2. So overall, you have 2n log 2. But what is the situation if those two gases were indistinguishable? If they were indistinguishable in the first place, so the presence of this membrane here doesn't actually make a difference, because from the very beginning, you would have 2n particles of the same gas filling up the whole volume. And even after you expand it, effectively you wouldn't get any difference. So in this case, the entropy produced would be 0. Now, the paradox came from the fact that one can imagine that maybe these two gases are only very slightly distinguishable, or maybe the degree of freedom that distinguishes them is not detectable by your apparatus. And so you have a limit in which they effectively become indistinguishable. And then you would have some discontinuous jump from this situation here, where you produce 2n log 2 of entropy, to the situation in which you actually produce nothing. So how to reconcile this paradox? There's been several studies in the past 50 years, I would say. Some resolutions to this were actually by realizing that maybe we are counting it wrong in the case in which the particles are indistinguishable. So some studies by founding fathers like Gibbs, Boltzmann themselves, they were just saying, actually, the way I've been presenting it, it doesn't look quite right because the entropy is not extensive in that case. So if we assign labels to each of the particles, they are not physical in the case in which the particles are actually indistinguishable. So suppose that, of course, for distinguishable particles, I could individually identify each of them in their state. And so the state space would have a volume V to the n. The entropy, if those states were distinguishable, would be, of course, the log of the state space. But in my case, I cannot. So permutations of the different particles would just count it as the same state. So I have to renormalize my phase space here by factor n factorial. And in this way, when I count the entropy from the number of microstates, then I would have something which in the limit of large n is actually extensive. This is the way people have been looking at this phenomenon before, but this is not what I'm interested in this talk. In this talk, we're actually interested in the operational meaning of this paradox. And this was, I think, very nicely understood by James in one of his papers on this paradox. So what he said is that actually this is not really a paradox, but it is corresponding to a physical situation which models the capability of different observers. So whether two gases are distinguishable or indistinguishable, it is in the eye of the observer. So it just means whether we have the facilities to be able to access degrees of freedom that distinguish them or not. If they are distinguishable, so if we can actually access those degrees of freedom separately, then this information that we have about them, so this entropy which is produced, can actually give us a product which is work. So we can extract work from this situation that is proportional to this 2n log 2, because of course we can couple to each of those two species of gas differently. For instance, through some semi-permeable membrane, which only lets one different species pass in one way or the other. And so we can actually extract as much work by coupling piston to this through the expansion of the gases. If, on the other hand, so the observer which can do this and can extract work from this system would be named as an informed observer. So he can access, or they can access these degrees of freedom. On the other hand, we can have an observer that doesn't have this facility, and so it is ignorant to the degrees of freedom that distinguish the two gases. And this ignorant observer, there's no way they can extract any work from this situation when we let the gases expand. So this difference in entropies is not just something artificial, but it corresponds to the capabilities of different observers when they are approaching and exploiting this particular toy model, which is gases in a box, in order to extract work. So he puts it this way: so the amount of useful work we can extract depends on how much subjective information we have about this microstate. So this is not a paradox, but a platitude. James was quite arrogant all the time, but I think it put this thing right. Now, we accept this understanding, but of course we want to go one step beyond, and then we ask, what's going to happen in case we model these gases fully by using quantum mechanics? So in recent years, many of you have been following the developments of the quantum theory of thermodynamics. So many of the fundamental laws of thermodynamics have to be adjusted. And a lot of discovery has been going on in order to understand how to properly take into account processing of resources in thermodynamics by analyzing what is the role of quantum phenomena like coherence and so on. And this has led to, as I said, revisitation of second law into many different second laws, which can be understood from a resource theoretic point of view, has led to novel protocols for work extraction empowered by quantum correlations, has led to novel models and experiments in implementing refrigerators, heat exchangers, thermal machines in general with just one or a bunch of atoms, so in the fully quantum regime. In this case, we are interested in the process of work extraction from gases, which might be indistinguishable or distinguishable depending on the capabilities of observers. So I want to find what are the fundamental limits on work extractable by different observers when we have the situation, so Gibbs mixing of bosonic or fermionic particles. Right, so I think in the talk I will mostly focus on bosons, but most of these things can be adjusted for fermions as well. So the way we develop this is as follows. I'll present a very simple toy model, and then I will show that it actually works by reproducing the results of the classical case, which I've shown earlier. And then we have to come up with a quantum description of the different observers. So being ignorant or informed, it means which operations that observer is allowed or not allowed to do. And then, of course, we look at the results. So is the quantum ignorant observer going to be more powerful than the classical ignorant observer? Yes, but you will see. Okay, so what is the model? Well, as before, we have a box with two sides, and then we ideally divide it in cells. This will map different configurations of the particles in, so it's a discrete grid of configurations. It's d/2 cells in each of the sides. And we start with n particles on each side, in this case, n = 3. Right, so we make the gases distinguishable. So of course, we have the degree of freedom, which is configuration, where each particle is sitting in each cell of the grid. But then we have an extra degree of freedom, which we might think of as spin, for instance. Just as if you want spin 1/2, so they can be up or down once we place them. Important thing is in this very, say, basic toy model, we are assuming that all cells are degenerate in energy. So if you want, this would correspond to having a Hamiltonian which vanishes, or you might think of a limit of a non-vanishing Hamiltonian when you have high temperature, so that effectively they're all degenerate in energy. This is fine because we can show it models the ideal gas or reconstructs the classical case. So we assume at the beginning, each of the two halves, the gases which are in there, are thermalized. And then we will see what happens once we let them expand and interact. So the informed observer is one that has access to the spin degrees of freedom. By having access, I mean, he can read them out, he can make measurements on them, but he cannot change the number of particles which are spin up or spin down, because that's conservation law. But they can at least access those degrees of freedom in the measurement. The ignorant observer cannot. So every dynamics that we model from the point of view of the ignorant observer has to be independent of spin. So we have to trace over those degrees of freedom. They can only access the configuration space. Okay, so as I said, is it too naive? What is the question is, can we actually extract work? So can we relate calculation of entropies in this model from actual work extraction? And the answer comes again from recent developments in thermodynamics from a resource theoretic point of view. So in the so-called resource theory of quantum thermodynamics, what the observers are allowed to do are thermal operations, which means you have a system, you can couple it with a thermal reservoir, so you can append as many other systems in thermal state as you want. Then you're allowed to, wait, do I have chance? Oh no. Okay, so you're allowed to do global unitary operations on system and all these additional reservoirs, so like work battery and so on, which have to be conserving the total energy. So energy preserving global unitaries, and then you can trace over the ancillas. All of these, they correspond to a set of quantum channels on your main system, which are called thermal operations. They've been well characterized. So under this framework, you can show that you can extract work from a system by using thermal operations, and this work is upper bounded by the difference in free energy before and after the process. So we will go and calculate difference in entropies there between initial and final states by means of the von Neumann entropies in the quantum case, with the idea that there exists some thermal operation which asymptotically allows you to extract as much work as kBT times that difference of entropy. So I will present results for the entropies, but you rest assured by this framework that there exists, at least in principle, I'm not saying that we can implement it in the lab easily, but there exist operations which give operational meaning to these entropies here, in the same spirit as Jane's in the classical case. Right, so it models the ideal classical gas in a way that I will just show in a moment. So if we want to see what happens in the classical case, then all these entropies, they can just be computed by counting configurations and microstates. So let's revisit the classical case. At the beginning, we have on each side a uniform distribution of n identical particles over d over 2 cells. At the final state, then, of course, we will have a uniform distribution of all the configurations of all the particles, 2n, over all the cells in this box, which are d cells. So we just have to count properly. So if the observer is informed, so they can distinguish the spin degrees of freedom. So configurations, so states where particles are in the same configuration, but they have different spin will be counted as different states. For the ignorant observers, those configurations will just be the same. So what are the results that we get here? Let's navigate through them. So at the beginning, we have n particles in each side uniformly distributed over d over 2 cells. Okay, so in one side we have n particles over d over 2, on the other side n particles over d over 2. And whether they are distinguishable or indistinguishable, it doesn't matter. So the entropy at the beginning will be just twice this factor here. At the end, after we have let the Gibbs mixing happen, then if they are indistinguishable, then of course it doesn't really matter whether we can or not access the spin degrees of freedom, because they actually have no difference. So there's no spin dependence in this case. So we will just have 2n particles uniformly distributed over d configurations. And this is this term here that you see in all of the three green boxes. But if, on the other hand, the particles are distinguishable and the observer can distinguish them, then they would see twice n particles distributed over d cells, because they will be two different species. And so in this yellow box, bottom left, then you see that the term for the final entropy, in this case, by an informed observer with distinguishable gases, will be different, actually higher. Now we're going to take some limits in order to recover what we have said before in the classical Gibbs paradox. And the limits are the following. First of all, large number of particles. So it's a kind of macroscopic limit. But on the other hand, also low density. So we have a lot more cells in the grid. It's kind of almost a continuous limit, continuum limit. So you have a lot more cells in the grid than the actual particles that fill them. If you take those two limits, then there's no entropy production in 3 out of 4 cases, where 0 means something going logarithmic in n, so which is of course vanishing compared to something going linear in n. Yeah. Well, on the other hand, for the informed observer with distinguishable gases, they can see a difference in entropy, which is 2n log 2, just like in the classical case. And as I said, so this corresponds to actual abilities to extract work from that system. Right, so now we have to model the quantum case. I still have a bit of time. In the quantum case, I'm not going to cover all of these cases separately, because if the gases are identical, there's nothing you can do. There's no work you can extract, they just mix. And if the observer is informed and the gases are distinguishable, this is also the best you can do. You're not going to improve this, but it's going to be very surprising what happens for an ignorant observer in the quantum case. So this is the case we're going to focus on. Right, so in the quantum case, now I'm going to go through a bit of maths here. We have to model things properly, taking into account the symmetries and the structure of the problem. So what we have here is as follows. The Hilbert space for a single particle is going to be a composition of two Hilbert spaces, one for the configuration degree of freedom, so the spatial one, and this one is a d-dimensional Hilbert space if there are d cells. Okay, so we assign basis states depending on which cell our particle sits. And on the other hand, then you have the spin degrees of freedom. As we said, this is just a qubit, so it's a two-dimensional Hilbert space. But on top of this, we have here particles that have to respect the exchange statistics. So overall, when we combine the Hilbert space for n particles, then depending on their nature, we have to consider projection onto the symmetric or the antisymmetric subspace, depending if they are fermions, bosons or fermions, respectively. So overall, the Hilbert space would be just projection of these big tensor products over the corresponding subspace. So when we're going to do permutations on different particles, then you will have composition of permutations on the configuration and on the spin state. But because they have to respect the overall symmetry, then these permutations will couple those degrees of freedom. And so we can effectively decompose our big Hilbert space for n particles in terms of subspace, which are indexed by a specific symmetry. So I'm giving an example here, for instance. If you have the simplest example that we're all familiar with, so if we have just two particles and two cells, then of course we have the spatially symmetric configuration of this particle is coupled with the spin symmetric triplet configuration, yeah, where there's up, up, down, down, and then up, down, plus, down, up. This is a three-dimensional subspace, which we all know is the triplet, and this will couple with the spatially symmetric configuration. That's an allowed state. On the other hand, the spatially antisymmetric configuration will couple with the spin antisymmetric configuration, which is the singlet. If we have fermions, then coupling is inverted. This will be coupled with this will be coupled with this to respect the overall antisymmetry requirement. So effectively, what we have been doing here is we have been decomposing our space into two subspaces, one that we call the singlet, one that we call the triplet, indexed by a quantum number that is like an eigenvalue of a total angular momentum operator. And this is easy to do. We all do it in the case of two particles, but in general, this can be done for the big Hilbert space of n particles by making use of the so-called Schur-Weil duality. So each specific symmetry of the wave function, spatial wave function, will be indexed by value of this coefficient. So we can decompose our Hilbert space in this way. We have to apply this thing twice. So once we apply and then we decompose into spatial and spin permutations configurations, then we apply it again to the spin case, which is by itself also an angular momentum, and then we get the following decomposition. So our Hilbert space for n particles can be decomposed into subspaces indexed by J, where this term Hx would correspond to irreducible representations of the unitary group of dimension D, and the other HS subspace would correspond to irreducible representations of U2. Right, this looks very good because we have effectively in this way explicitly decoupled within each subspace with a given J, we have decoupled the spatial and the spin degrees of freedom. So now what we know is we have to model the capability of this ignorant observer. And in this way, it is transparent because the ignorant observer can only access the spatial degrees of freedom, has no control over the spin ones. So now we have to input all these conditions to determine what are the operations that the ignorant observer can implement on the system. So the dynamics that the gas can, the dynamics that our system can undertake will be constrained if we are not able to access the degrees of freedom of spin. So overall, I said our observer can implement thermal operations, which correspond to global energy preserving unitaries on system heat path, work battery, and any additional thermal reservoir if needed. So this U has to be energy preserving, but for the ignorant observer, there is more because it only has to act on this specific subspace. And overall, then we also have the fact that it needs to preserve the exchange symmetry, of course. So if you combine all these ingredients together, it is easy to see that this specific subset of channels conserves our quantum number J. So what it means that the thermalization happens independently within each subspace with a given special symmetry J. So according to the informed observer, the system was initially thermal in each of the halves and then can just fully thermalize through the Gibbs mixing. But according to the ignorant observer, this cannot happen. We can only let each individual subspace thermalize. So the state of the system as described by this observer with limited capability is just a mixture, which can be written as a direct sum of states, each living in this subspace for a given J with certain probabilities that we can work out. And now as a consequence of this Gibbs mixing, each of those evolves independently within its subspace because J is conserved for these operations. Okay, so this is what happens. We start from a state like this, and then it evolves so that it thermalizes within each subspace. And we cannot just send it through a general thermal state because this violates the constraints that we have for this observer. I think I do have a, okay, so now what we need to do, we need to calculate the difference in entropy before and after. So the before is always the same. As we said, in the end, the state has evolved into this mixture of local maximally mixed states. So the entropy at the end is just given by sum over J, Pj, ln of Dj, where Dj are the dimensions of each of those subspaces, and Pj's can be computed from composition of angular momentum. So effectively, we are treating groups of spins on one side and groups of spins on the other side as two large spins. And then from the Clebsch-Gordon coefficients you obtain from combining this angular momentum, you can calculate this. I have all the expressions in the paper, but I'm not going to put them on the screen because they're just ugly combinatorial things. And similarly, you can get the DJ from the Schur duality, so from representation theory. We have all these formulas. We can just analyze them now in useful limits. So first of all, this quantity, it cannot exceed the entropy difference for the informed observer, which was equal in the classical and the quantum case and was just given by this. That's the best that they can do. But interestingly, this can be larger than the corresponding classical ignorant observer's case. And as I said, this is not just, calculating stuff from number theory, but it will translate into a work extraction that on average is given by KBT times this entropy difference. On average, why I say on average? Because of course there exists some thermal operations subject to these constraints, which extracts given amount of work within each subspace with a fixed J. Then overall, the average work that can be extracted, we can calculate by mediating over this with this probability. So of course, we have that there is this fluctuating quantity. So work in this case is a fluctuating quantity, but on average will correspond to this physical entropy production. Now, this is also, I don't know if I have it here or later, so I also comment on whether not just, okay, the average work is maybe that, but is it feasible that we can actually extract this in practice? And the answer is yes, because you will see that the fluctuations around the mean are negligible. So effectively, there's not too much variation between these different subspaces in the amount of work that we can actually extract. So it is probabilistic, but it almost is deterministic in this case. We will see in a moment. Right, so for example, let's consider this situation. So we have, again, two cells, two particles, so one particle per side. And then we're going to write the initial state where we have one spin up at the left side and one spin down at the down side. You can manipulate this state, and it just becomes a superposition of this form. So you will have here effectively one state that belongs to the J = 1 subspace, if you want the triplet one. And then you have here the singlet state. Now, this would be the initial state. Once you let the system undergo the evolution, each of the subspaces will thermalize independently. So the singlet subspace is only this state, so it will remain the same. It's not going to change. On the other hand, the state in the j equal 1 subspace will evolve towards a mixture, a uniform mixture of all the three basis states in this subspace. So at the end, the entropy production would be, because there are three here, so it would be 1/2 ln of 3 plus nothing here. And so you see it is non-zero. So the ignorant observer can witness something in this case, even without having access to the actual degrees of freedom of spin. Right, so we can actually make some plots in order to analyze this quantity and look at the limits. So let's look at these plots. These are for bosons. I have similar ones for fermions. And we are plotting here the difference in entropy before and after the Gibbs mixing as observed by different observers. Now, this upper bound here would be just 2n log 2, which we know is the limit in the classical informed case. The classical ignorant observer, we know will converge to 0 in the appropriate limit. So these two plots on the left is just small n, on the right is larger n. So remember, we need large n and even larger d to work out the limits we want. So d is increasing on the horizontal axis. This, as we know, there's nothing the ignorant classical observer can do. But on the other hand, the gap between informed and ignorant observer in the quantum case gets actually smaller and smaller with increasing d. And it can be calculated exactly analytically in the limit in which d is very large over n and n is also large. That gap tends to 0. So in the relevant limit, in the quantum case, both the ignorant observer and the informed observer can actually extract the same amount of work from the system, which is completely different from the classical case. So the capability of the ignorant observer, without having access to that degree of freedom that distinguishes the two gases, tend to be the same as the capabilities of the fully informed observer. So if we go back, as I said, to the issue of deterministic versus probabilistic work, we can work out the variance around the mean for work extraction in these different subspaces. And in the usual limit for large number low density, this variance is actually a constant. So it is negligible compared with the mean that scales with n. So I can go back to the original table. I can fill it in now. All those cases, they remain 0 because for indistinguishable gases, there's nothing we can do. But if they are distinguishable, and an informed observer can extract 2n log 2 kBt work from the system, a quantum ignorant observer in the appropriate limit can extract as much work as the informed one, while for a classical case, ignorant observers has nothing to do with it. So interestingly enough, that's very puzzling because the maximum difference between classical and quantum thermodynamics in this specific phenomenon appears in a macroscopic limit where you would think that maybe the work would just become classically, but it's actually not the case. So if I have time, I think I probably just a couple of minutes to try and explain why this thing
yes,
is working.
Gerardo, please go on. Please go on, and then you will have some.
Okay, yeah, I don't want to take time off questions, but
no, it's fine.
Okay, let's see. Right, so we have said, let us focus on this low density limit. So there are a lot of cells, most of them will be empty. So there's almost no, at most you would think that there's one particle per cell, yeah? So let us consider that, for instance, we have 2n particles. They will not have double occupancy if there are so many. That is the actual low density limit, so with high probability. And so we will just consider configurations which are corresponding to, say, the first, we just give labels to the cells. So the first 2n cells will be the occupied ones, and all the others will be empty. So for this spatial configuration, a spin configuration is just going to be a permutation of n particles with spin up and n particles with spin down. The question is, if we do not have access to this spin part, how much information do we lose? So remember, this reasoning holds specifically for the low density limit. As you see, you reach there as a limit. For higher density, then of course things are more complicated. But in this case, everything just reduces to Hilbert space of 2n qubits. And we can apply the same trick as before. So apply the Schur-White duality, and then we decompose it into subspaces where we have here a component that runs over the irreducible representations of the special unitary group dimension 2, and that this would be for the spatial part. And then on the other hand, you just have the other subspace, which is irreducible representations of the spin, of the SN and all possible permutations of the cells. So a basis for this Hilbert space can be written as we do with the normal angular momentum, but noting that the last one is corresponding now to the group of permutations. So a basis for this decomposed space can be written in terms of the Schur basis, in terms of 3 quantum number J and P. So J would be again corresponding to the spatial symmetry. M would be like an eigenvalue of the total Z component of the spin, and P would correspond to the permutations. But now the idea is, if you are ignorant, then you do not have access to M, to the M part. So you cannot operate on one of these subspaces. But the point is, if you ignore M, you have nothing to lose because M was fixed anyway. It's just the difference between number of particles up and number of particles down, which, as we said, was conserved. So you cannot change this, even if we have access to spin degrees of freedom. So once you decompose things in this way for the low density limit, you realize that all the basis states in this Schur basis can be distinguished by the ignorant observer, even if you do not have any access to the spin itself. And you can come up with examples, for instance. So for 2 particles, then there are 2 distinguishable states. This would be again singlet, like this symmetric and antisymmetric state, singlet and triplet, perfectly distinguishable without having to actually measure the spin. And this you can do by sending them through a kind of beam splitter, as I will say in a moment. For for 3 particles, so n equal 3, then the idea is states in the Schur basis are perfectly distinguishable without accessing the spin component. Maybe states in the original configuration spaces will be a lot more complicated, but there exists a basis in which they are all distinguishable without having to access that. And so for this reason, in this limit, you do not lose any information by not having access to the spin degrees of freedom. So what I wanted to say first, that the analogy in quantum optics is as follows. Suppose you have 2 photons, and then you want to distinguish whether they have the same or different polarization, but you only have a non-polarizing beam splitter and photon counters. Both of these things would correspond to capabilities of an ignorant observer with respect to the polarization. But actually, if you send them through, then you will know that if you only get the 2 particles at one side or 2 particles at the other side, then at the beginning they had the same polarization. Or if you just get the other configuration here, so you will, so 1, 1, 1, 1. So then you know that they had different polarization in the first place. And so it is possible to distinguish these cases without having to have apparatus which are sensitive to that particular degrees of freedom. And the situation with the gases is exactly the same in the low density limit. Right, so there've been, I think this is it. So there've been other works recently about thermodynamics with identical particles, which are interesting to look if you want. But just to summarize, in the quantum mechanics, there is some relational spin information that you can imprint upon degrees of freedom which are observable. But you can distinguish superpositions of configurations which are classically indistinguishable, even if you have not any access to that particular degree of freedom. I try to explain very quickly at the end why this works. So in the most extreme macroscopic case, in the low density, you can get as much from an ignorant observer as from an informed one. And this is our version of a fully quantum Gibbs paradox. And interestingly enough, so you cannot say that classical thermodynamics emerges in the thermodynamic or macroscopic limit, because actually there you have the maximum divergence between the 2 cases. So we can look at variations of this with more realistic models, and actually how to implement the operation that extract work in practice. This may be very complicated because it means that your ignorant observer needs to rotate the system in the Schur basis in order to extract the information that they want. But to implement the Schur transform is of the same complexity as the quantum Fourier transform, which enters, say, in Shor's algorithm. So it might be that actually realizing this might be as complex as implementing universal quantum computing. So we have not come up with some simple way to actually implement in the lab this work extraction from an ignorant observer, but we are working on finding approximate ways to still do better than the classical case, even though we cannot reach the optimum one. I think that's it. The paper appeared a few months ago in Nature Communications, and this was done with two indistinguishable Benjamins, like last time. So Morris and Yadin, they are now distinguished. They work in different places, but at the time they were both in Nottingham. Thank you.
Okay. Thanks, Gerardo, for this great talk. So now we open the space for some questions. There is some time for a question. Does anybody in the audience? Sebastian 14 has a question. Please, Sebastian, go on.
Hello.
Hi.
Thank you, Gerardo, for the very interesting talk. I have a conceptual question. I want to know what do you think about the possibility to think that the description of the ignorant observer can be considered as a gross description of the fine description of the informer observer. This is a possibility, or they are fully incompatible?
No. I think that's fine. Because if you see here, what we need, it is definitely that. So it depends where you put this fine graining. Yeah. So once we had written all the states in this way, let me see. Yeah. So in general, in principle, you can have all states of this Hilbert space, but the problem is the ignorant observer does not have access to one part of it, so it has to trace over those degrees of freedom, and so only has access to a limited set of operations that conserve this constraint, and will describe the dynamics with the limited set of states which are confined within that subspace. So it is, in a sense, as you say, you are neglecting some degrees of freedom. So it is like a coarse-grained version of what the informed observer can do, which is only constrained by having to use thermal operations and the exchange symmetry. It does not have this additional requirement. Of course, in this case, we only have spatial and spin. You might think of some more complex situation where you have several degrees of freedom, and maybe you can do this progressive coarse graining, as you say, by having observers with different intermediate capabilities. They can distinguish some of them, but not all of them. And it would be interesting to see whether we have a hierarchy of possibilities and whether this is very special in this case, or whether they all converge, even when you have more degrees of freedom, whether they all converge to the full fine graining capabilities once you limit the access to degrees of freedom. I don't know if this answers your question.
Yes. Thank you very much.
Thanks.